Okay, let's look a little more closely into what happens when we do algebra with cycles. Now, what do I mean by algebra with cycles? I mean, the cycle represents a permutation, and permutations have the composition operation. So we'll see what composition does to cycles. First of all, let's look at powers of cycles. For instance, consider the product of 1, 2, 6, 4, the cycle 1, 2, 6, 4 with itself. All right, so I've written a representation similar to what we've done before. 1, 2, 6, 4 is here, 1, 2, 6, 4 is here. So for instance, what does 1 go to? Well, the first cycle takes 1 to 2, and then the second cycle takes 2 to 6. Now you might think that the power of any power of cycles is a cycle, but that's not actually what happens. If you take a look and see what happens, you end up with this permutation, surprisingly. You can verify that yourself. For instance, let's verify 2 goes to 4. Well, 2 here goes to 6, and then 6 goes to 4. Okay, so in fact 2, 4 is correct. You'd have to verify what 6 goes to and what 4 goes to, and that would verify that the power of 1, 2, 6, 4 is 1, 6, 2, 4. Okay, so very interesting. Okay, so let's consider more what happens when we do this. Okay, so here we have a cycle. And these are exercises for you to try yourself to get familiar with this concept. And it turns out that if you take a cycle and you successively raise it to powers, eventually you get back to the original cycle again. And that always happens. All right, so you'll find that out through experience. It's almost like turning a wheel. You know that if you have a wheel and you turn it, eventually you get back to start again. So you can kind of think that whenever you apply a permutation cycle, it's like turning a wheel 1 notch. Okay, so if you keep turning the wheel, every time you multiply again by that permutation, you're turning the wheel another notch. Eventually you're getting back to start. So it makes sense that there should be some number k which gets you back to the start. And in fact, this number is equal to the length of the cycle. Right? Think simply of the triangle. Here's a case here. If I take this, if I have the cycle 1, 2, 3, okay, you can verify that this squared is going to be 1, 3, 2. And if I take 1, 2, 3 cubed, well, then 1 goes to 2, 2 goes to 3, 3 goes to 1, so 1 goes to 1, 2 goes to 3, 3 goes to 1, 1 goes to 2, 2 goes to 2, and 3 goes to 3, so that's equal to the identity. Okay, so it really does make sense that the order of a cycle is equal to the length of the cycle. If I raise a cycle to a power equal to the length of that cycle, then I get the identity back again. And here's a formal algebraic proof for you to fill out. All right, now we've defined order. Order is equal to the smallest power that you can raise a permutation to get the identity back again. So we've seen orders of cycles. The order of a cycle is equal to the length of a cycle. What about other permutations? Well, let's formalize this definition. The order of a permutation is the smallest positive integer such that that permutation to that power is equal to the identity. Okay. So, for instance, if I take, let's take another simple example. Let's take the permutation 1, 2, 3, 4, 5. Okay, so let's just call that sigma. All right. If you do this, you'll find out that sigma squared is equal to let's see, it's going to be 3, 5, 4. You can check this yourself. Sigma cubed is equal to 1, 2. Sigma to the fourth is equal to 3, 4, 5. Sigma to the fifth is equal to 1, 2, 3, 5, 4. And sigma to the sixth turns out to be the identity. So you can verify these things. In this case, the order of this permutation is equal to 6. All right, now, here we see that sigma to the 6 is the identity. Now, you can think also that sigma to the 12th. What about sigma to the 12th? Well, that would be sigma to the 6th, compose sigma to the 6th, but sigma to the 6th is the identity, so it should be identity composed identity, which is still identity. What about sigma to the 24th? Similarly, any multiple of 6 should be a power that takes sigma back to 0. And that's what this proposition says. If the order of a permutation is k, then t to the l is the identity if and only if l is congruent to 0 mod k. In other words, L is a multiple of the order of the permutation. So you'll have a chance to do that proof. Okay. So here's some examples you can try that out on. Okay, some other algebraic examples. All right, now this figure is supposed to be a conceptual aid for you to understand the order of a permutation. Okay, so suppose you have a permutation that has 1 4 cycle, 1 5 cycle, and 1 6 cycle. Wait a minute, 1, 2, 3, 4, 5, 6, yes. It has 1 4 cycle, 1 5 cycle, 1 6 cycle. Now if I do that permutation one time, what's it going to do to this cycle? Well, it's going to take this 1 and gear it up over here. It's going to take this 1 and gear it up over here. It's going to take this 1 and gear it up over here. Notice that these gears are all connected, so each gear is going to move one position. Suppose I do so that's taking the permutation once. Suppose I take the permutation again. Well, the ones are going to move. This one here will end up over here. This one here will end up over here. This one here will end up over here. Now suppose I do 4 times. Well, if I do 4 times, this one ends up back here again. So that looks like the identity. However, this one has shifted 4 positions. 1, 2, 3, 4. This one is over here. And this one, 1, 2, 3, 4. This one is over here. Okay, so I don't have the identity. This cycle gives me the identity. The other twos don't. So the question is, how many turns do you have to do in order to get all 3 gears back to the start again? Well, from the theorem we just mentioned, to get this gear back to the start, I would need to have a multiple of 4. According to this gear, I would need a multiple of 5. And according to this gear, I would need a multiple of 6. So I would have to raise this permutation to a power that's a multiple of 4 and of 5 and of 6. Okay, so in fact, if I took, I need a number that that's divisible by 4, 5, and 6. And you can see that, let's see, does 60 work? I think 60 works. All right. Is there a smaller number that works? Well, you can figure that out. Okay. So here we're exploring this idea. In fact, for 2 cycles, it turns out that the order of the product of disjoint cycles is simply equal to the least common multiple of the 2 orders. Now you can notice something about 60 here and the least common multiple of these 3 numbers. So you can see how this is going to generalize. In fact, that general proposition is here. You can read this. This example relates to the example that I just showed with the cycling gears. All right, so now we're going to talk about transpositions. We've talked about cycles in general. It turns out that the simplest possible cycle is something like 1, 2. That's a 2 cycle that takes 1 to 2 and 2 to 1. Okay. And it turns out that all cycles can be built up out of these simple 2 cycles, which we also call transpositions. So 2 cycles are the building blocks. Okay. So we can multiply 2 cycles together and get larger and larger cycles. Okay. And this shows how you can build up large cycles from transpositions. Here's an equation that expresses an n cycle in terms of several transpositions. And you can imagine that if any n cycle can be expressed as transpositions, a product of transpositions, that pretty much tells you that any permutation at all can be written as a product of transpositions. Okay, and that's what this says. Okay, and the way you find out how to write this permutation as a product of transpositions is you take it cycle by cycle. And each cycle can be written independently as a product of transpositions. Now we can use this transposition representation to find the inverse of a permutation. The inverse of a transposition itself is the transposition. Okay. And the inverse of a product of transpositions, well, you can figure that out. There's a way to show that. All right, so you'll investigate how transpositions relate to inverses of permutations. All right, so we'll stop there.